I'm back with another session of creative coding. This time I'll show you how to recreate this piece of motion graphics. Some of the techniques are not new. You've probably seen me demonstrate them in my earlier videos, but rest assured that you'll find lots of unseen stuff too. In the end, that's what creative coding is, recombining existing concepts to make something new. I'll try to explain everything as clearly as I can without making the video too long or boring. The key idea here is a spiral curve coiled around a central ring. Let's start with a curved circle, followed by a join geometry node. Add a set position node and join both geometries. This node works on control points. We want to offset them in the normal direction. Normal is a vector attribute that is automatically generated for every curve in geometry nodes pointing away from it. Apart from normal, curves in geometry nodes come bundled with another vector attribute called tangent, which points in the direction of the curve. So flipping the curve direction means changing where the tangent vector points to. Both vectors stand perpendicular to each other and form a coordinate system for each point along the curve. Tilting, on the other hand, represents the angle at which the normal vector rotates around the tangent direction. Normal and tangent vectors are automatically calculated the moment you generate the curve. Blender takes care of that for us, but we can control the tilting amount using the set tilting node. This node expects an angle expressed in radians, but we'll drive it using the curve factor. We'll map the factor range from 0 to 1 into a new range from 0 to a multiple of 2 times pi, which is a full rotation. Multiply by 5. This wraps the outer curve 5 times around the original circle. That was easy, wasn't it? Not only do we control how many times one wire ring wraps around the other, but we can set the coil's radius too. Raise the resolution of the initial circle to smooth the coil curve. How do we generate the line segments that connect both wires? Split a new geometry branch from the original circle and convert it to mesh. Now add an extrude mesh node and choose vertices from the options drop-down. This operation generates the lines and expects a direction vector and a length value for each one. The tilted normal would work great as the direction for extrusion. Feed a normal node to it. Nothing changes. The problem is that after the conversion to mesh, the vertices lost all the information stored so far under the curve control points. So the normal vector is not present to direct the vertex extrusion as it should. But that's where the capture attribute node comes to the rescue. Let's store the normal vector as a point attribute for the curve control points before the conversion. Feed the captured attribute to the offset input of the extrude node. Join geometries together. See? Now we have connected both the center ring and the coiled one with straight mesh lines. In my video, I changed the length of the segments along the curve based on the tilt value. Again, to have this attribute available for the mesh, we capture it before the geometry conversion. Remember, the tilt attribute stores at each control point an angle with a value ranging from 0 to 5 full circles. Feeding this angle into a cosine operation returns a value ranging from 1 to -1. We'll drive the extrusion offset scale with it. This creates a wavy pattern around the circle. For more control, map these values to a new custom range from -1 to 1 to -0.25 to 1.25. Let's now animate this coiled wire revolving around the center ring. To do this, we'll add to the tilt attribute. Insert an add node, scroll the empty value and see the geometry evolve. We'll drive this value with our scene frame number. Map it from 0 to the total frames of our scene into a range from 0 to a multiple of 2 times pi. This means that during the course of the scene, we'll add another full circle to the tilting angle. one or more in fact, to be precise. Hit play and see the coil come around. To smooth the outer wire, you might want to set the spline type to NURBS. And with that, the core of the setup is finished. Let's now generate the spheres. Their position will also be based on the spiral curve. Spread out another geometry branch and add a resample node. Set the count number to 10, twice the amount of the spiral rotations. The points stay attached to the spiral and animate with it. It's easy to instantiate the spheres on those points. Add an instance on points node with a UV sphere as an instance. In my example, I rotated the spheres inwards as they traveled along their orbit. Let me show you how to do that too. I'll delete every other row of polygons so the rotation is visible. Insert a delete geometry node in face mode. We'll drive the selection of polygons to delete with their index number, divided by the number of segments per ring. Connect an integer node to the segments input of the sphere node and then connect it to the divide node. Floor the result, then do a modulo operation by 2. This will mark every other row of the sphere for deletion. Now let's align the spheres so their poles aim towards the center. Each sphere position is a vector that starts from the center. Add a position node into the rotation input of the instance on points node. Use an align Euler to vector node to rotate the y-axis so it matches the cross product of position vector and the z-axis. Insert a rotate Euler node. Select local coordinate mode. We'll want to rotate around a single axis. Select the axis angle mode and set the y component to 1. Slide the angle value and see the spheres rotate around the local y-axis. We'll use the same angle we animated earlier for the tilt to rotate the spheres. Drag the output of the range map node into the angle input. Hit play and observe the result. If you need them to rotate faster, just multiply the result by a factor of 2. And that's where I leave you. Feel free to experiment with your own values. I would love to see what you come up with, and if you like the video, please share the knowledge.